So today we are covering chapters 6 through 8, a few questions from each chapter, a few exercise questions from each chapter, and we are starting with chapter 6. And again, I'm going to scroll to the answers. I posted this on Canvas, so you may have already seen these questions. I didn't post the answers, so I'll post answers later. So classify each of the following species as a nucleophile or an electrophile. Nucleophile is electron pair donor, so it must have at least one free electron pair. If it has more than one, it's still a nucleophile, but it can donate only one of those electron pairs. And electrophile is electron pair acceptor, so that means it must have an empty orbital. Frequently, charges are associated with nucleophiles and electrophiles, negative charge with nucleophile and positive with electrophile, but charges don't make species nucleophile or electrophile. So, first one, I showed electron pair. They may not be shown on the exam, so you need to know if electron pairs are present. But here they are represented, and you can see this is a nucleophile, so 2 free electron pair. Also, if you have been reading a little bit in advance and have been reading chapter 9, you know that pi bond is also acts as a nucleophile because pi electron pair can be donated. Sigma bond is that single bond, minimum bond between the two atoms. And any excessive electron pair, so that of double, that makes bond double or triple, 2 excessive electron pairs, can be donated to an electrophile. That makes species nucleophile. So this is nucleophilic in 2 ways, because it has free electron pair on oxygen, electron pairs on oxygen, and carbon-oxygen pi bond. So a nucleophile. Next one is neither nucleophile nor electrophile. Sometimes students list this as an electrophile because nitrogen is positively charged, but it cannot accept an electron pair, so it's neither nucleophile nor electrophile. Next species is just like the first one, a nucleophile, and again for 2 reasons. First one, because it has free electron pair on nitrogen, and second, carbon-nitrogen pi bond. Either of them could be donated, depending on the reagent. Next, we have an electrophile, zinc ion. So this is zinc 2 plus cation. Obviously, it has an empty orbital. Metal cations have empty orbitals, so that's an electrophile. Next one, zinc chloride. That's zinc with 2 bonds to chlorine. So obviously, 2 orbitals are empty. Zinc doesn't have octet, even though it's a transition element. We can use that rule, octet rule, roughly. Or alternatively, you can look at, that's more accurate, to look at electron configuration of zinc, because a lot of electrophiles actually have empty d orbitals. For some of these common metals, you can use like for something like zinc or actually main group metals. Zinc is not main group metal, it's kind of close to, I think that there is well, copper, for copper, copper and zinc, there may be, for those groups, there may be a little bit of dispute whether they are transition metals or not. But in any case, if d orbital is empty, then it's also an electrophile. And a lot of species are electrophiles, like phosphorus, because they have empty d orbital, those with phosphorus atom. So in this case, we have an electrophile. And then obviously a nucleophile, because there are free electrons on sulfur. And finally, an electrophile. This is main group element, main group metal, group 13, aluminum, and so empty orbital on aluminum. So those are nucleophiles and electrophiles. And you need to know which is which, because in polar reaction, it's a nucleophile that reacts with an electrophile, and bond is formed between a nucleophile and an electrophile. Also, you may recall in chapter 5, these identical, same species were part of question 8. Exactly the same species. And Lewis acid is identical to an electrophile and Lewis base to a nucleophile. Concepts of Lewis acids and bases and electrophiles and nucleophiles were developed at about the same time. But at the time, those chemists were not communicating with each other, and so They were in different areas of chemistry, and so we retained these terms. But actually, Lewis acid is identical to an electrophile and Lewis base to a nucleophile. Every Lewis acid is an electrophile, every Lewis base is a nucleophile, and vice versa. Electrophile Lewis acid, nucleophile Lewis base. Okay. And then next question is actually application of the previous one. Which of the following undergoes reaction with water? Well, water is a nucleophile. So really question is which one is an electrophile? Or if we look at definition of electrophile, electrophile must have empty orbital. So ultimately question is which of the following has an empty orbital? And first one is carbocation. Carbocation has empty p orbital. So A is correct answer. Next is obviously a nucleophile, free electron pair on nitrogen, and no empty orbitals. Here that's amine. Third compound C is an ether, again an electrophile, a nucleophile, free electron pairs on oxygen. And finally, the last one, actually, this one is an electrophile, but very weak one. It is an electrophile because of the very weak carbon-chlorine bond. Sorry, it's a weak electrophile because of the polarized carbon-chlorine bond. No, making lots of mistakes today. Sorry about that. So carbon-chlorine bond is polarized, and carbon has partial positive charge or partial electron deficiency. And so carbon actually is an electrophile, but it can react only in specific kind of reactions. Those are substitution bimolecular nucleophilic substitution reactions, where we have very strong nucleophile that is capable effectively of pushing the chlorine out. This is something we'll cover in chapter 12. And until then, you should ignore those kind of electrophiles. So we'll cover nucleophilic substitutions in chapter 12. And so until then, you should ignore those kind of electrophiles. And anyway, this compound, chloromethane, does not react with water because water is not strong enough nucleophile. So in this case, we have nucleophile that is relatively weak or at least moderately strong. And so that one will react only with typical strong electrophiles that effectively have an empty orbital. So you don't need to worry about something like this. The reason I'm mentioning this case D is that we will encounter it later in the course. And so as you are studying, then let's say preparing for the final, that could be confusing. And the other is that maybe some of you are using other materials to study or are having a tutor, and that person may notice and say, hey, look, D is an electrophile. So how come he is giving you just this rule, which one is electrophile? So those are the reasons. And let me see. Yeah, the last one is on the same topic. Let's finish the last one, and then I will answer any questions you may have. So water is a nucleophile. Sorry, I'm reading previous one. Yeah, I'm really a little bit out of it right now. Which of the following cannot be protonated? And then you have four species. So proton, H plus, is obviously species with an empty orbital. If it's species with an empty orbital, it's an electrophile. And so it protonates nucleophiles. So proton reacts or protonates nucleophiles, forms a bond with nucleophiles. That means that this question is, if something cannot be protonated, which of the following is not a nucleophile? And then again, you turn it into an ultimate question. Definition of nucleophile is that it has a free electron pair available for donation. So which of the following does not have electron pair available for donation? Ether, electron pairs on oxygen, that one has electron pairs available. SH, we have just seen this earlier, this is thiol, it has electron pairs available for donation. BH3, this one has actually empty orbital, this one is an electrophile. Two electrophiles are electron deficient, they cannot react with each other, so that's correct. And the last one is trimethylamine, or it was supposed to be let me fix that, trimethylamine. So it has free electron pair on nitrogen, it can be protonated. Okay, and let me fix this D in the original question. Okay. Okay, so let me see. Yeah. Before I do question 4, it's a little bit different topic. Let me see. Okay, are there any questions? Okay, so let's go back and finish exercises on chapter 6. So 4, shown below is a reaction diagram for a hypothetical reaction. How many steps are in the reaction? That's question A. B, which species is the kinetic product? And C, what is the thermodynamic sink of the reaction? So those are a little bit more advanced concepts of chapter 6. Those are the ones at the end of the chapter 6. So let's look at A. How many steps are in the reaction? So it was labeled under the original question that R stands for reactants, I for intermediates, and P for products. You can see from this diagram that in the middle is R, reactant, or reactants, if there is more than one. So that's where the reaction starts. And there are two possible pathways. Pathway to the right goes through this transition state. Transition states are maxima on the reaction diagram. They have not been indicated here. Sometimes we label them as TS, like TS1, TS2, and so on. But here it will be a little bit difficult to because we have two different intermediates, intermediate 1 and 2. And then if this is TS2, what is this? And TS1, and so on. So simply transition state leading to intermediate 2. Transition state leading to intermediate 1. Transition state leading to product 1, product 2. So reactant, and so from this diagram you can see that there are two possible reaction pathways. Pathway to the right that goes through intermediate 2 to product 2, and pathway to the left that goes through intermediate 1 to product 1. So how many steps are there? When you're counting steps, you're counting how many transition states there are, because each transition state represents one step. So you're looking how many local maxima there are on a diagram. And so starting with reactant, there is one transition state, 2. There are 2 transition states. For one reaction pathway, also 2 for the alternative. So there are only two transition states. So reaction has 2 steps, 2 reaction steps. Frequently, particularly in more advanced textbooks, we represent it like this, those 2 steps. So reactant, and then 2 possible pathways. In introductory course, we often use representation, this on top, because this one often confuses students because of the overlapping lines. But both are in use. This one also sometimes confuses students because I end up sometimes on a test with answer how many steps there are, 4, because students simply assume that the reaction starts at the left and then 1, 2, 3, 4. So look at labels, and if axes are indicated, they don't have to be. But if they are indicated, then on the horizontal axis, it may be indicated whether there is reaction progress or whether reaction starts here. And of course, vertical axis is assumed to be energy. They're not indicated because it's always assumed that vertical axis is some form of energy axis, and on horizontal, there is reaction progress, but it may start at the left or it may start in the middle of the graph. So there are 2 steps, 2 transition states, 2 steps. And then second one is a little bit tricky. Which species is the kinetic product? So kinetic product is one that forms faster. And then question is which one forms faster, because of course faster is one that goes through lower energy transition state. So when you are looking at reactant, it goes through this low energy transition state, lower energy transition state to go through to intermediate 2, then to intermediate 1. Intermediate 2 is lower in energy than intermediate 1. And transition state going to intermediate 2 is lower in energy to that going to intermediate 1. And so intermediate 2 forms faster than 1. For that reason, sometimes students would guess that then eventually that ends up being product 2, that's kinetic product. No, because that actually doesn't matter. Formation of intermediates actually in this case doesn't matter, because we have another step that has higher energy transition state. Formation of intermediates would have mattered if this second step was lower in energy compared to transition state, was lower in energy compared to the first one. But in this case, it is higher. So when you're looking at reaction pathway and you're looking at kinetic versus thermodynamic control, you're looking only at rate determining step. And rate determining step, it doesn't matter how many steps there are, 2, 3, 4. Rate determining step is one that is highest in energy. And so for each of the pathways, looking at either diagram, it's the second step that is rate determining, not formation of the intermediate. That's low, that has low energy of the transition state. Is the second one that has high energy of the transition state. That's rate determining. Same goes for the alternative pathway. It's second step that is rate determining. Or you look at it here. So the pathway to the right is still shown here, this one in black, here in blue to the left. So blue one that leads to product one, that has lowest energy transition state. When we look at transition states of highest energy for each pathway, it's one that leads to product one. So that's the kinetic product. And finally, which one is the thermodynamic sink? Thermodynamic sink is a point on the energy diagram that is the lowest in energy. And if reaction is allowed, in theory, if reaction is allowed to run indefinitely and temperature is high enough to allow for equilibration, then all of the material will eventually accumulate in thermodynamic sink, will end up in thermodynamic sink. That's why it's called thermodynamic sink. And P2, that's P2, that's the lowest point. That's obviously thermodynamic sink is identical to thermodynamic product. So it's thermodynamic product. And from this, you can also draw a conclusion that a short reaction time and low temperature will favor kinetic product, because at low temperature, reactants will have just enough energy to overcome these lower energy transition states and go to product one. They probably won't have enough energy to overcome this high energy transition state. They would need higher temperature and more energy. So that's below temperature, and short reaction time to prevent equilibration, because product one could equilibrate and revert back to reactants. Because even though activation energy for reverse reaction seems to be high, it's comparable to this one. So if this reaction can occur, then reverse reaction here can occur too. And so short reaction time doesn't give reaction time or reactant products time to revert back. And so short reaction time and low temperature favors kinetic product. Conversely, long reaction time and high temperature high enough so that reactants have enough energy to overcome high energy transition state, and long reaction times so that there is enough time for equilibration so that everything can accumulate at P2 favors thermodynamic product. Okay, so this completes this brief review of short chapter 6, and I will end recording here.